All right, the final concept that I want to talk about is geometric probability. Geometric probability, or probability in general, is always going to be a value between 0 and 1. 0 means what? No chance. 1 means it's always going to happen, right? So when you look at this, you're looking at some decimal value. The decimal values can correspond to percentages or fractions as well, but often the probability is just a form of a number from 0 to 1. And so if I gave you this circle here and I asked you, assuming this entire thing is shaded, if I had to give you this circle and I asked you what is the probability that you could randomly pick a point in this circle and it falls in the shaded region, what would the answer be? Okay, the probability would be 1. And that corresponds to 100% chance, or a fraction of 1 out of 1. Okay. When you're looking at geometric probability, the actual calculation itself is a fraction of the desired outcome, or outcomes, over the total possible outcomes. Okay, so on this one here, the technical or the mathematical calculation is, assuming you have this circle pi r squared, the desired outcome is the shaded region, pi r squared. The total possible outcomes is the entire circle encircled in red, which also is pi r squared. And so this all cancels to give you a 1. What's going to happen if we do something like this? Okay, so if we shade in this portion of it, okay, again, you can identify this probability without having to calculate. What is the probability here? 1/2, which in decimal form is 0.5, or 50%, or 1 out of 2. Again, there's multiple ways to express probability. But if we're looking at the calculation for it, we can still look at the area formula for our semicircle, which is 1/2 pi r squared divided by the total pi r squared. And so those wind up canceling, leaving just our 1/2. Here, this entire thing canceled, leaving just the 1. And so as we work with particular forms, so let's say we work with the sectors. And let's say this is an 80-degree arc measure. Okay, what would be the probability of randomly picking a point in the shaded region of this circle? Technically, if we're setting up our entire calculation, our probability is the sector, 80 over 360 times pi r squared, over the whole circle, which is pi r squared. Well, again, we can disregard that form. The factors of 10 cancel. What goes into both 8 and 36? 4 goes into 2, or 4 goes into 8 twice. 4 goes into 36. 9. So you wind up with 9, or 2/9, which is 0.22 repeating, okay, or about 22.2%. Again, the 2 is repeating. Or we have this rational form, 2 over 9. Those would be the 3 different ways to express that probability. Okay, so when you're dealing with just that one single shape, not bad. Okay, the probability is going to get a little more challenging when you have overlapping shapes or shapes within shapes. Okay, right now, you're pretty much limited to just circles and dissected circles. So let's take a look at what you might see. Okay, what if I gave you something that looked like this? Two circles, they meet at the center point. And I ask you, what is the probability of randomly picking a shaded region here? Looking at this, the desired outcome is the shaded region over the total region, which is shaded and unshaded. Okay, so when you look at this, the easiest one to figure is the total, right? What shape is the total region? The whole thing is just a circle, right? So let's look in terms of this circle. And usually when you do this, it's easiest to designate your smallest piece first. So let's assume that the radius of our small circle is x. What does that mean the radius of our larger circle is? 2x. So if we use our area formula, we have pi times r squared for our total. And what does that actually reduce or simplify to? 2 squared is 4 pi x squared. So there's our denominator, the total area, shaded and unshaded together. Okay, how would we find our shaded region? Subtract the two small circles from the large circle. So we already know what the large one is. We calculated that here. So here's the large circle, 4 pi x squared. And from that, we're going to subtract 2 of the small circles. What would the area formula be for each individual small circle? Pi times x squared. And so now when we simplify this, what's 2 pi x squared minus, what's 4 pi x squared minus 2 pi x squared? 2 pi x squared. And so now when I simplify, the x squareds cancel, the pi cancels, 2 over 4 reduces to 1/2, and so our probability is 0.5. Okay, so there's a 50-50 chance of randomly selecting a shaded point compared to the unshaded. Okay. Let's see if you can kind of follow this one. The probability, once again, of randomly picking a point in the shaded region. Assuming these are 4 congruent circles in here. Okay, so if we let the smallest piece be our unknown, so x is the radius of our small circles, what does that mean the radius of our larger circle is going to be? 1, 2, 3, 4 x's is the radius of our large circle. So here we're going to take the area of our entire thing, the denominator is pi times the radius, 4x squared. What does that simplify to? 16 pi x squared. So here's our denominator. And then the desired outcome is the shaded region. So to find the shaded region, we do the same thing as before. We take the whole thing and we subtract the smaller circles. So the whole thing was 16 pi x squared. We want to subtract 4 circles. Each circle has an area formula of pi x squared. And so 16 pi x squared minus 4 pi x squared gives you 12 pi x squared. Here your x squareds cancel, your pi's cancel. What goes into both 12 and 16? 4 goes into 12, and 4 goes into 16. And so you get your probability to be 0.75, or 3/4. And so you have a 3/4 chance of picking a point that falls in the shaded region. Okay, now let me talk about a couple different ways that you can approach this. Okay, one possible way that you can approach this, different than what I did right here, is you can still use the probability, set up the denominator the same way that we did here. If it's easier to find the unshaded region, which in this particular case it is, right? The unshaded region would simply be 4 times pi x squared. So if all we did was we found the unshaded region, the x squareds cancel, the pi's cancel, we're left with 4 over 16, which reduces to 1 over 4. If 1/4 is the probability of being unshaded, what's left for the probability of shaded? It would have to be 3/4, right? So you can do it that way as well. Here it's one or the other. So when you're looking for probability, you can find the probability of whatever's easiest to find, and then translate that or manipulate it to find whatever other additional information is needed. Okay, there's one other way to approach this that can be really quick, and it's not going to be understood by all of you, so that's okay. But that is using ratio of parts and ratio of areas. Okay? If you look at the small, or between the small circle and large circle, what's the ratio of parts? X to 4x is 1 to 4. What does that mean the ratio of their areas is going to have to be? 1 to 16. So what that means is each of these small circles is 1/16 the area of the large circle. Well, how many small circles do we have? 4. So 4 times 1/16 gives you 4/16 of the whole. And that reduces to what fraction? 1/4 of the whole is unshaded. So what fraction is shaded? 3/4. So if you understand the way that the ratio of parts and areas can relate, you can wind up solving the problem very simply just with some quick mental calculations.